I would give you a short quiz Thursday morning. It'll be only about half a period. Couple questions. Then there may be another one in about 2 weeks. Since 2 weeks from now I'll be gone that week, and so
You'll have somebody else.
somebody else can give it for me.
I got this. I think 123.
Open book or
I
what?
haven't even started on my.
Which kind do you want?
Well, we want an open note on neck Tuesday.
You do, all right. Okay, I'll give you a short quiz Thursday morning, about 2 questions, or I don't know how many it'll be, but might have more than one part to each question. And I'll let you use your notes Thursday morning.
It would be like problems we've already had.
Perhaps. Well, it certainly should be related to those, or something like that order, but yeah. Well, I might say a word or two about the last problem set. First of all, I'd mention that Mr. Joe Aliotto, a graduate student who took my course last year, has graded the problem set 3, and I think he perhaps graded them generally leniently. Although I think I have been doing so far. Also, on the first 2 sets, perhaps more leniently than I would be on examination, because and I might make a point or two about some of the, well, specifically one error that's commonly made in that, which one? The second problem, yeah. The second problem, which you were asked to calculate the vapor-liquid equilibrium as if ethyl alcohol and water were an ideal mixture, and then compare it with the actual vapor-liquid equilibria from known data. The logical type of a curve to compare it with would be the vapor-liquid equilibrium curve, of course, expressed as mole percent or mole fraction for both liquid and vapor compositions, because that's what you're calculating here. Several people plotted their data on the boiling point composition diagram that I handed out, which was plotted as volume percent alcohol on the horizontal basis. So it's rather difficult to make a valid interpretation when you mix units again and plot mole percentages on a graph of volume percent. One or more went to the trouble to convert correctly, apparently, the mole fraction values for an ideal solution over to weight percent and then to volume percent, and plotted them on the curve that way, which I guess is correct, but it's a rather laborious way of doing it when you had the vapor-liquid equilibrium curve already at hand and already plotted. So that it was intended to simply illustrate that the fact that if we have the true vapor-liquid equilibrium curve for ethyl alcohol and water looks something like this, We have the azeotrope here, whereas this would be the true or experimental values. And if it was an ideal mixture, the curve would have been in something of this order. This would be for an ideal solution. I guess I haven't drawn this very too closely. Then I ask you to compare or discuss the relative ease of separation for an actual mixture of, if it was 25 mole percent, which is over about here, compared to what it would be for an ideal mixture. And so since the distance away from the equilibrium here, from the diagonal where x is equal to y, is sort of an indication of the volatility, or it is directly a measure of the volatility for a particular mixture. And since at 25 mole percent, the true value is considerably above the ideal mixture, that means then in practice that it's much easier to separate alcohol from water at a 25% concentration than it would be if it were an ideal mixture, because the curve is well above the diagonal, well above the ideal curve. On the other hand, and I guess I didn't draw this very well, but but anyway, for a 75% mixture, the actual curve is below what would be for an ideal mixture. It's approaching the azeotrope here, sort of almost tangentially. So at high alcohol concentrations, as represented by 75 mole percent, it's more difficult to separate alcohol from water than it would be if it were an ideal mixture. Another sort of common error, I consider an error in writing solutions, is simply to put down something and then not clearly indicate what this says. It may be in this. Maybe your answer is in the sequence in which the question was asked, but some people said, well, it's easier to separate. Well, what's easier to separate? If you don't make a statement, I don't know that you understand what I ask for. So, generally speaking, when you answer questions, you should make it can be very simple and short, but you should, whatever statement is made should be clear as to what you mean. If it's a comparative question, an answer, such as this was, then you have to say, it's easier than what? Are there any questions about that problem set? Now, last time I handed out a little sheet which referred to mathematical treatment for flash distillation.
Ready to see what it looks like?
There's a little single-page handwritten notes here, and simply showed a little schematic diagram of the flash distillation process, which we have classified as a single-stage, continuous or steady-state process in which the vaporization is considered to be conducted in so that the vapor is evolved from the liquid under equilibrium conditions. And so we simply, by writing a material balance for volatile component, came up with a simple expression that y relating y to x, y is equal to f minus 1 over f times x plus x sub f over f, where f is simply a symbol for fraction vaporized, which of course is simply the amount of the vapor divided by the amount of the feed. The amount vaporized with reference to the feed, amount of the feed. You might note also that if you multiply the amount of the vapor by the concentration of volatile component in the vapor and divide by the feed, multiply by its concentration of a particular volatile component, that this is simply the fraction of the volatile component recovered. Recovered in the vapor. In the vapor stream. But now referring to this equation that I've just written here, this relationship, if we consider that, that's a plus sign, if we're considering a situation whereby we have a stated fraction vaporized, well, of course, F, or the fraction vaporized, is a constant term, and of course then this is a constant, and of course the feed composition is usually stated as a stated condition, so that's a constant. So we have an equation here which relates the composition of the vapor, the concentration of the volatile component in the vapor, to the concentration of the volatile component in the residual liquid, the equilibrium liquid. And so this is simply an equation of a straight line, isn't it? Y is equal to mx plus b. So equation 1 is a straight line, is equation of a straight line. Of slope f minus 1 over f. Now, in order to locate a straight line equation on a graph of some kind, what do you need to know? Besides the slope, you have to know what?
1 point.
1 point. And so you can solve, so the one way to find 1 point is to you can let y is equal to 0 and solve for x. You let x equal 0 and solve for y. That'd give you the intercepts on the 0 axis, either vertical or horizontal axis. Or if you let y equal to x and solve for x, as I've done here on this handout, you'll find that that when x is equal to y, the value of x is equal to x sub f, which says then that this line here passes through a point on the diagonal, if we're considering an equilibrium curve plot, at a value of x equal to y at the value of x sub f. Or in other words, if we want to draw an equilibrium curve plot here, where we plot x on the horizontal axis and y on the vertical, and invariably we draw a diagonal in here for reference purposes for x is equal to y. this equation would has to pass through this point on the diagonal where x is equal to y at a value of x sub f. And it can be readily seen that if you, for finite values of, reasonable values of the fraction vaporized, which can only vary between 0 and 1, that the slope is negative. For example, if the fraction vaporized is 5/10 or a half, the slope would be 5/10 minus 1 divided by 5/10, or minus 5/10 over 5/10, or 1. So in that case, the equation of a straight line would have a slope of minus 1 and pass through this point. So it'd be a curve something like that. This would be y is equal to f minus 1 over f times x plus x sub f over f, this equation number 1 here. Well, note that this equation number 1 is an equation which is determined by what we call the operating conditions. The operating conditions being, in this case, fraction vaporized and concentration in the feed. So consequently, we call this equation, sometimes call it the equation of the operating line, or the line or the relationship determined by the process conditions. If we're applying this to a process which we have stated that we are making the assumption is carried out under equilibrium conditions, of course then another relationship that has to be satisfied is what? Vapor-liquid equilibrium itself. And so the second relationship, this is indicated down at the bottom line, bottom 2 lines on that handout. If we want to solve a particular situation for values of y or x or both, then this has to be satisfied. Equation, let's see, this equation 1 has to be satisfied, and secondly, vapor-liquid equilibria must be satisfied. Well, in the usual case, of course, vapor-liquid equilibrium is available or presented in the form of tabular data or graph. Most often the tabular data is not capable of being expressed by an algebraic equation, so we express it by plotting it as a graph. For example, if this is the equilibrium curve, we have this relationship then. There's one condition, condition 2 here, and the straight line which represents the process conditions represents the second condition. And so for a particular situation, the values of y and x would be given by the intercept of the two relationships. The intercept of this operating line with the equilibrium curve. Now this would be the typical way, this would be the more general way of applying this principle to a solution of problems. Yes?
Could you repeat that last statement about what happens when you combine the equilibrium curve with the actual processing intercept the two?
Well, this we said this is the equilibrium curve, and we said this equation here, which we derived as representing the operating conditions, which is a straight line, for that particular operating condition, the situation to be is satisfied when the two lines intersect, and so that's for this particular way I plotted here, which is roughly when f is 5/10. This point here would be the value of y of the vapor given off, and this would be the value of x for that particular situation.
In other words, you have to combine both equations to get the real.
To find the answer to a particular problem or situation. Yeah.
Now those two only combine at that one point, so that's only good for when f is equal to 0.5.
That's right. If this is if this represents a curve that's for 5/10, f1f is 5/10.
That means that
And of course, if f was, let's say, if f was 5/10, the slope is -1, isn't it? If f was 2/10, 20% vaporized, well, what would we have? We'd have 2/10 minus 1 would be -8/10 divided by 2/10, it'd be -4.0, right? If this was 8/10, for example, 8/10 vaporized, you'd have 8/10 minus 8/10 divided by 2/10, or minus 2/10 divided by 8/10, or minus 1/4, or 0.25 would be the slope of the line. Now, if you had for this particular case, then the slope -4, to plot the curve, you draw a line to this point. So we said that whatever the value of the fraction vaporized, it always passes through the value of x sub f. And so to locate the point, you'd simply move over here one unit horizontally and 4 units vertically, and locate a point up here and draw a line like this. So for this, the slope would be -4. For this one, the slope is -1. Similarly, for this one, it'd be a line which would have a slope maybe like so. Well, yes?
I'm just trying to understand what y stands for. I can see what x sub f is. But y, when you plot over to the left there from that point, upper point, you get y. Now what is y? When you find y, what do
Be the concentration of the volatile component we're talking about in the vapor given out. I didn't read this is given on your handout, but we'll draw another little sketch here. If we have this represents the flash chamber where the vaporization takes place, and we introduce a feed in here, usually through some heater or some device which has increased the energy, and then it either goes through a pressure release valve or maybe under vacuum, reduced pressure, and we separate the liquid into a vapor stream and the liquid stream. And of course, this liquid stream has a composition of X, and the vapor stream has a composition of Y, and that's what we're talking about. That's what we're talking about. Mm-hmm.
Does each one of these lines with different slopes then, when you just draw there, define essentially a different operating condition?
Yeah. The way I did here, I drew 3 lines which represents 3 different operating conditions with respect to the amount vaporized. And then of course for a constant value of x sub f, I didn't change that on my
Different operating change.
different operating fraction vapor.
Right, changes in some respect.
That's all.
So by different operating conditions, you mean the different amount of vapor when it enters that flash chamber? After it's
Well, the different amounts of vapor that's removed in reference to the feed rate. The fraction vaporized.
the fraction vaporized in the first heater or inside the distillations? There's going to be some
Well,
vaporization in that heater.
No, We don't allow it to be vaporized. We keep it under pressure, so it's still in a liquid phase. Let's say.
So it enters under contact, and as soon as it hits the,
Well, if it did vaporize, we're not. If there was some vaporization here, it'd still be. We still make the assumption that it's vaporized under equilibrium conditions in here. The liquid level might be like so. Say this would be the liquid, and this would be vapor passing off.
percentage vapor in there, the X of
It's a
that.
fraction of this feed that's passed off as vapor. If you're running 100 pounds, and you say the fraction vaporizes 5/10, it means 50 pounds of that 100 goes off as vapor. That's all.
You're saying that X of F is always the same, though?
No, yeah, I mean, well, it is for the situation I plotted here. You can have different problems with different X of F, but that'd be a separate problem usually.
You have one flash equilibrium distillation. For that distillation, X of F is always going to be the same. Is that what you're saying? Or does it change as you distill?
No, we're talking about a steady state process. That's one thing you have to comprehend now, is that we're talking about a continuous or steady state process. So for a particular process, the composition of the feed would be the same, not be changing. Otherwise, it wouldn't be a steady state or steady process.
So the composition of Y and X stay the same for any particular
Yeah.
operating conditions in the same feed.
That's right, as long as the fraction vaporizes the same. In other words, it's the composition of the vapor and the liquid streams leaving the process are independent of time. That's what we mean by a continuous process, steady state process. Do not change with time. Well, finally, as I indicated down at the bottom of that page, I believe, we need two relationships here: the operating conditions, and secondly, the vapor-liquid equilibria. As I said before, that's either in the form of a graph, or B, in some limited cases, especially when we're talking about very dilute solutions that we might be interested in, sometimes like flashing off the trace volatiles out of a feed material, such as people are interested in collecting the volatile components of fruit or vegetable juices. Usually the components in that case would be of such dilute concentration that they can be frequently expressed by a limited relationship that the Y is equal to some constant times the concentration in the liquid. Or in other words, what we call Henry's law, or K would be Henry's constant. And so there may be limited cases in which you can solve a problem algebraically by using this as a second relationship. As a matter of fact, I just happen to have some exercises to illustrate these principles I've talked about.
Do you have any static questions for the camera?
What to do with them? Yeah, I found them. Almost thought I'd forgotten. Mm-hmm. Sure, you can take one of these and pass them along.
Wednesday? How will you study for the quiz?
This is due
on Thursday too?
This is partly studying for the quiz, working the problems.
Oh, there's gonna be some of these kind of problems on the quiz?
No, not necessarily.
Oh.
So you have three problems here illustrating flash equilibrium distillation. And I'll give you a couple hints here. I'll give you a couple hints about the procedure on this, but it shouldn't take you very long. First one here has to do with a binary solution containing 20% by weight of ethyl alcohol and water, and that's the feed material. So X sub F is 20% or 0.20 mass fraction. And it asks what are the mass percentages or mass fractions of alcohol in both the vapor and liquid streams when the following for each of the following mass fractions of feed vaporized. 0, 0.25, 0.5, 0.75, and 1. And so those are the values of F. Now, a little problem here, or a little question of semantics perhaps. When you talk about 0 feed vaporized, well, you could conclude that there's no vapor, so but then the answer would not be that the vapor would be 0 concentration. If you want to be absolutely argumentative about it, you can say there's no vapor, so the problem doesn't apply, but the problem is not realistic. But you can consider it that what is the composition of the vapor as the fraction vaporized approaches 0 as a limit. And that's reasonable, isn't it? That's reasonable.
Could you run that by again?
I'll start out here by. I'll continue this little table here, which is the way you'd start out working this problem. If you have 0, well then as a fraction vaporized, this would be. What would this value here be? It'd be -1 divided by 0 would be infinity, wouldn't it? So the slope of the operating line would be a vertical line, where the slope's infinite. It'd be a vertical line. So that right there would represent the operating line when the slope is infinite. And so you can continue on down through here until you get to 1. And the fraction vapor, when the fraction vaporized approaches 1, or complete vaporization, why then, of course, 1 minus 1 would be 0 over 1, or this would be 0. So the slope goes all the way from infinity down to 0. The slope of a 0 would be a line that's horizontal, wouldn't it? That'd be the slope of 0. And so you can say still solve the problem algebraically or graphically, because when the slope is infinite, such as this, the operating line intersects the curve at a value of y, which is the same as x sub f. Or in other words, vertical. That's supposed to be a vertical line. And no, as the value of x would be equal to x sub f, because you really are not taking anything out. So the stream going out would have x sub f in it, wouldn't it? But the composition of the vapor, if there was an infinitely small amount of vapor given off, would have this composition, wouldn't it? Similarly, for 0, as you approach 0 amount vaporized, why, of course, as it approaches 100% vaporized, what I'm trying to say, where the slope is 0, then the composition of the vapor approaches this value here, Or in other words, it'd essentially be what's in the feed would be in the vapor. But if there was a little bit of residual liquid, it would simply be this value here. Oh, this value here, wherever it intersects the curve.
What equilibrium curve do you want? The ideal curve or the actual curve?
Actual curve.
Yeah, the one that you handed out in the sheet.
True data. So that brings up the next point. As I say, a hint here, carefully plot the equilibrium curve using mass percentages up to about 20% by weight. Any higher values are not needed because obviously we're going to be concerned with the equilibrium curve only to the left of x sub f. Because you see in every case here the slope is negative. It's over on the left-hand side. And also, this question here is given in mass percentages, so there's no need to worry about converting to mole percentages, because you can plot the equilibrium curve on a mass basis. I gave you a table of data a few periods back, table of equilibrium data, in which mass percentages as well as mole percentages are given in the table.
The other sheet we got,
And so here's my solution. I'll show you almost about how it could look. I used maybe a little larger scale than necessary. I tried to use so I get the maximum size here. In fact, I extended it actually a little beyond the graph paper here in order to make it work. 20% here. Need up to about 60%, or a little about 65% on the vertical scale. So I used a different scale vertically and did horizontally. This is the x is equal to y diagonal here. So you plot 4 or 5 values of weight percent here and draw a curve through it. That's the equilibrium curve. Then you draw these lines in here with the various slopes and read the intercepts off the curve. That's all. That's the answer. Those are the answers. So I've almost solved it for you.
The line through the points, the equilibrium line?
This one happened to be an extraneous one, not part of the problem. I wrote that on, or put it on there before I realized it. Were these operating lines, like here's f is equal to 0.25, the slope would be minus 0.75 divided by 0.25, or minus 3. So here's a line of the slope of minus 3. And so you simply read off the values of y and x where it intersects the curve. Simple as that.
And that the equilibrium curve is from the curve we already have here.
I haven't given you any plotted curve on a mass basis. I gave you only the data, so you'll have to plot your own. And so you can solve this problem just by doing what I did here, and then this is the answer right here, a little table showing f minus 1 and x and y values. And so there's the whole solution right here. See? Now the second problem here is a case where we have said that within the range of operating conditions specified that we can adequately express the vapor-liquid equilibrium curve by a relationship that y is equal to 10x. I believe that's what it was, 10x. Yeah, on a mass basis. And so you have a question here of introducing a feed into a first stage, which you get off a vapor, which you call V1 to distinguish it from the first stage, and the liquid passing off here, which we call L1. And then the problem shows that this is introduced into a second stage, and this gives off a vapor which we'll call V2 and a liquid called L2. So you're asked to find out what the composition of this X1 is, and Y1, and Y2, and X2. Where the fraction vaporized in this case the fraction vaporized is 0.25, and over here the fraction vaporized is 0.35. When I say the fraction of the fraction vaporized, of course we're talking about the fraction of the feed. So note here that if you let F equal 100 or let F equal 1, that the amount going into this one is not 1, it's some fraction of that. Or in other words, it's 0.75 of F would be the amount here. That's important when you try to answer the second part, part B. No, it's important to answer part A too.
So the second little f is 35% of 75.
Yeah, that's right. That's right. Okay, well, let's see what you can do with that now. Well, the problem 3, I might give you another hint on that one, was that you have to introduce a third relationship, which I've already given, that the percent recovery, of course, would be equal to, in any particular stage, would be equal to vapor times its concentration divided by the feed times its concentration. Percent recovery, or of course times 100 if you want percent. All right, that's I think this is probably all we'll need to say about flash or equilibrium distillation until I see how you get along with your problems.
Or don't get along.
Now what I intended to do was begin the introduction of how we treat. Well, any questions about this? That's a kind of a messy graph I drew there, but kept. Now, the next subject we want to discuss is the next type of distillation in our little classification of kinds of distillation. In other words, I had down here the kinds of distillation first was continuous or steady state, and then we had single stage, or this flash distillation, which we've just been talking about. Now, secondly, we want to take up the more important consideration of continuous fractional distillation, or rectification. And I guess I'll start out by mentioning that we already have the basis for at least qualitatively understanding the process of fractional distillation. From a graphical standpoint, we have already indicated, if we have an equilibrium curve here, this is the diagonal, and have some equilibrium curve, whatever system we're talking about, that if you want to think of it in this fashion, that suppose we take a liquid of a certain composition, X of F, and feed it into some type of an arrangement or apparatus in which we can have successive stages of vaporization. Well, what happens if we bring this? If we introduce this feed into a distillation system and vaporize it under equilibrium conditions, or under complete equilibrium conditions, the curve tells us that the vapor given off is given by this value here, which we might call Y1 if you want to, since it's the first stage of vaporization. Now, if we take that vapor and condense it, well, then we're back to a liquid phase again. And the composition of the liquid phase then that we'd have available for the next vaporization would be given by projecting this over to the diagonal where x is equal to y. So now we're back here to x1. We'd call that x1. And so we're ready to start over. So now if we vaporize a liquid of this composition, it gives off a vapor of this one. So we might call that y2. And similarly, by condensing that to a liquid, we'd have x2, and so forth. So you see, if we could conduct a process with repeated steps of vaporization and followed by condensation, and maintain these conditions, we would see that it takes so many steps here to approach the purity of the more volatile component as we approach the top of an apparatus, or the top stage. In reality, of course, this condition would only be met when we have what we call total reflux or total equilibrium. If you were conducting this kind of thing in a distilling column where we had a discrete number of plates here and have a condenser up here, we have a number of stages here. This would only apply when we have no feed being introduced. The feed there'd be no change because of feed, and be no product being taken out. In other words, if we had a finite value of liquid on these trays, it's boiling and the vapor condensed and running back here. In effect, we'd have this sort of situation, whereby if we took samples off each of these stages and without disrupting the equilibrium, we'd find that they'd be represented by these values here, and so forth. Until, as we get considerable number of stages, we'd find here toward the top that the change in concentration is small, but because it's approaching the pure component. Well, of course, in reality, we can't conduct the process under total reflux. We have to introduce material to be separated, a feed material, and we have to take out product if we're going to accomplish anything. So the conditions under which we introduce the feed and conditions by which we remove the products determine how much change we get for a given stage of vaporization. In reality, we will find that when we develop this a little further, that we have what we call operating lines again, comparable to the term I used here applied to flash distillation. We will be able to develop a system whereby we have an operating line which represents the process conditions, and then we'll have an operating line for the stripping section of a column. If this is the feed, we call this a stripping section, as you recall. And up here, the concentrating section, concentrating or enriching section or the rectifying section, all those terms are used, applied to this. We'll have an operating line that may look something like this. If we desire that this be the product, X sub P, we have to have some finite reflux ratio. In other words, over here we had an infinite reflux ratio. We'd have, if they were talking about the ratio of the amount of liquid run back to the amount of product taken out, we'd have, if we have no product taken out, well, we'd have L over 0 would be an infinite reflux ratio. And that's the only special situation where this first chart I've shown would apply. So in reality then, when we have what we do have, and when we have finite ratios, is that, and I'll guess it, I'll try to sketch this once more, and if we have certain feed mixture like so indicated by X sub F, we will find that for a given product composition in this rectifying section, we have an operating line which does not coincide with the diagonal, but it intersects the diagonal at a value of X sub P and has a slope which is something less than 1, less than ideal. And similarly for the stripping section, we have to have some measurable or theoretically measurable concentration of the volatile component in the bottoms product going out here, which schematically then we'll represent by X sub B. And we'll find that there'll be an operating line which will have a slope greater than 1 for this section. And depends on operating conditions, it'll be located something like that. And so we have now that if these are the operating lines for the two sections, this will be the concentrating section, and this will be the operating line for, for the stripping section, that what happens is that if we start with a feed composition X sub F and introduce it under certain conditions so that we can determine where those points intersect, we will find that we go up here to the equilibrium curve as before to find out what the composition of the Y is in equilibrium with X sub F. But the amount of concentration affected in a stage with a finite reflux ratio is given by drawing a line over to the operating line. This line here, the operating line, represents values of Y and X. These are the values of Y. Y is equal to some function of X. This operating line. It's a straight line again, as I've drawn it here.
I think the X sub F is a little over. Is that supposed to, is this supposed to go through that point right there?
Not necessarily. Under one special condition it does, in most cases it doesn't. So I didn't...
It's just the same kind of thing we've had before where you go to the left.
In other words, if you have a liquid of this composition and cause it to be vaporized, this would be the composition of the vapor, the Y value. When it's condensed, it has a value here of, let's say, X1, if I was starting at this point. This would be Y1, this would be X1. Now then, if it's revaporized again, we get Y2 and we get X2 by condensing it. And so forth, we take our steps here until we have sufficient steps to span the required separation over to a value of X sub P. And it can be shown that to the left of the point of intersection of these two curves that we'll have steps between the curve and the operating line which indicate the number of steps required to do the stripping, to remove the concentration down to the specified allowable limit in the bottoms product. Now, next time we will go into how we arrive at, how we quantitatively locate these lines, so we can actually, in application, either calculate the number of stages required in the stripping section and the concentrating section to effect a given separation, or in the reverse process for a given particular piece of distilling equipment, we can determine what the composition would be under various conditions where you have a fixed number of steps to work with.
You can determine from the number of steps how much you're going to get out.
What concentrations you're going to get out,
Right.
and what reflux ratio you might have to use, things like that.
What's the point where the two operating lines meet?
Well, it's simply called the point of intersection of the two operating lines.
Well, what do you get from that? Anything?
Well, it means that where these two operating lines intersect, it means that to the left of the point of intersection, you take the steps between the curve and this operating line, not the projection of that one or the projection of this one, but in other words, I could stop drawing those at that point, you see. So, and so, I mean, when I do that, and you frequently draw the lines on beyond through the point, beyond which they apply.
So you take to find the Y, you take from XF all the way up to the equilibrium line.
Yeah.
And then you draw over
Yeah.
to the operating line.
I hope this will become clearer after our next period or two. Because